This lesson deals with Zener diodes and a shunt regulator. You can find these notes in the ECE302 ebook in Chapter 2 starting on page 72. Diodes that are designed with adequate power dissipation capabilities to operate in the breakdown region are called Zener diodes and are commonly used as voltage references or constant voltage devices. The symbol for a Zener diode is shown here, and it is the symbol of a diode but with two bars added. If we were to plot the voltage across it and the current through it, we would get our standard diode curve with a forward biasing in the first quadrant of some V sub D on, and then a breakdown voltage. Breakdown voltages for silicon can be somewhere from, say, 50 volts to several hundred volts to even 1,000 volts. But with a Zener diode, you're able to pick the value of this. You can pick this to be 6.8 volts or other voltages that are way smaller than 100 volts. When we buy a Zener diode, we intend to use it over here, so let's do the following. Let's take and reverse the directions of the voltage and the current. So I'll call the voltage from cathode to anode V sub Z, and the current I sub Z. This is going to be any voltage versus time and any current versus time. But by doing that, the first quadrant here becomes the third quadrant here, and then this third quadrant becomes the first quadrant. Now if you look at this symbol, and of course this one here, that looks like these extra bars on the Zener diode symbol. Suppose that we straighten these lines out, and likewise over here. When you're in the first quadrant here, we have really our model we've had before of an ideal diode and a battery, and that's really what this is here in the third quadrant. So let me propose the following model for a Zener diode. I'll use an ideal diode and a battery VD on, and then when we're in the third quadrant, I'm going to put the same thing but in the opposite direction. I'll call this voltage BV here V sub Z. Let's see if this model actually works. When I'm in the first quadrant, the current that's coming in here is I sub D, and that's greater than or equal to 0. That current can only go this way. Let's guess that this diode is on and this diode is off, and let's see if it's consistent with that. If D1's on, we're going to short it. If D2 is off, we're going to put an open circuit. If I sub D is positive, then I sub D1 is positive. The current in this ideal diode is greater than or equal to 0, so that checks. What about the voltage across V sub D2? Let's go around the loop and see what its value is. The rise in voltage is VD2, the drop is minus V sub Z, minus VD on, and back where we started. That's this equation here. But V sub Z is a positive number, VD on is a positive number. This is less than or equal to 0, and our guess checks. What about the third quadrant on that VI characteristic on the previous page to the left-hand side? If we're in the third quadrant, the current I sub D is negative. In other words, it's coming in this direction. The diode D1 can't be on, that's where the bar is. Looks like D2 would be on, so let me guess that D2 is on and D1 is off. Place this by a short circuit, and the voltage across the cathode anode would be equal to V sub Z, but from anode to cathode, which we're calling V sub D, would be equal to minus V sub Z. I'll see whether diode 1 is off. Let's go around the loop. The rise in voltage is VD1. The drop is minus V sub Z minus VD on. But V sub Z is positive, VD on is positive, and so this is less than or equal to 0, so the guess checks. In this previous two cases, we had one diode on, one diode off. Where are both diodes off? That's when the current is equal to 0. That sounds like the region between V sub Z and VD on. So let's see if that works. Let's put an open circuit here, an open circuit here, and see whether that's consistent with the region we need to cover yet, which is that straight line with 0 current. Let's go around the loop here and see if this is off. But I'm going to go around the outer part of this. So the rise in voltage is VD1. The drop is V sub D minus VD on. Now that needs to be less than or equal to 0 to be off. Let's do the same thing for VD2. Let's go around the loop this way. The rise in voltage is VD2. The drop is minus V sub Z minus V sub D. That needs to be less than or equal to 0. Take the first equation and put this on the other side of the equation. So V sub D would be less than or equal to VD on. And this equation here, let's solve for V sub D by putting this on this side of the equation. So V sub D would be greater than or equal to minus V sub Z, and that's this equation. And again, this is the region between VD on and V sub Z where the current is equal to 0. We are covering all of the regions on that piecewise linear model. This will be our model for a Zener diode. As I mentioned before, we usually pick a Zener diode to use it as a Zener diode. In our model, we saw that only one diode was conducting at a time. If you were operating in that third quadrant of V sub D versus I sub D, we're looking at the case where we had the diode D2 and V sub Z, and the diode D1 would be off. If you are going to use it in that third quadrant of V sub D versus I sub D, the other term in our model would just be an open circuit, and we just leave it off. Sometimes we just save ourselves a little bit of work by just using this as our model. But remember, there is something here in case current wants to flow in the other direction. So current can flow this way, and current can flow this way. I saved this till the end of the chapter because I know this is confusing. Let's take a look at what's called a shunt regulator. This consists of a voltage source, a Zener diode across the load, and then a series resistor. Shunt in electronics refers to parallel, so this is in parallel with the load. Suppose that this isn't a physical resistor, but a circuit that's hooked up here that draws a current given a voltage and has a ratio of voltage to current of, say, 150 ohms. And suppose that that changes to 125 ohms. Could you find the voltage across the load and the current in the Zener diode? This is a 1N759 Zener diode. If you look that up on the web, find its datasheet, that is a 12-volt Zener diode. The Zener diode can only absorb power. The only source of energy here is the 15-volt source, so current's going to come out of its terminal and try to come back this way and try to come back this way. Of course, you can do that. We're going to guess that we're operating in that Zener region where it looks like 12 volts. The voltage across the load is 12 volts, is the Zener voltage. And the current that's in here is just simply Ohm's law of 12 volts divided by 150 ohms, or 80 milliamps. Let's solve for the current in this resistor. The rise in voltage is 15. The drop is I30 times 30 plus 12. We could solve for the current in this resistor, where's the difference of two node voltages, 15 minus 12, divided by 30 ohms. That's 100 milliamps. There's 100 milliamps here. And there's 80 milliamps here. I could do a formal Kirchhoff's current law, but pretty easy to see that this is 20 milliamps. And our guess checks. The current is flowing from cathode to anode. Suppose that the load changes. But if this was 125 ohms, it would again be the voltage across here and the current through the Zener diode. We have 12 volts across the load because this is bigger than 12, so current's going to flow in this direction. And the current that flows in the load is going to be 12 volts now divided by 125 ohms, or 96 milliamps. We've got more current in here. Current in here is still the difference of these two node voltages divided by 30, and that's going to give me a current here of 100 milliamps, just like before. Now there's only 4 milliamps in here. Our guess checks having current flow in this direction. What would happen now if we were to make this resistor smaller? Well, it's going to want to draw more current. Where's the point where we get to the transition point of the Zener diode? And that's going to be when this current is the same as this one. When the load is 100 milliamps at 12 volts, we'll take all of this current and put it in the load, have nothing left here. And that'll be 120 ohms. This is going to regulate the voltage across here as long as the resistive load is a little bit bigger than 120 ohms. Let's go back to the original circuit and take a look at it as a word description. So we can describe how the circuit works in the following way. The Zener diode, when it's on, gives me a constant current in this resistor. In this case, it was 100 milliamps. As the load is varying, it takes some of that 100 milliamps and distributes it to the load. What's ever left over goes into the Zener diode. And it works as long as we don't try to take all of this current in the load. The power dissipated in here is the product of the voltage and current. And that varies depending on what's going on out here. The worst case is when you take the load off, all of that current flows into here. And these are Zener diodes and a shunt regulator.